So if the barometric pressure at sea level is 760 millimeters of mercury, oxygen exerts a partial pressure based upon its percentage of the atmosphere. What do we call that? Armando, do you remember?
FiO2.
Yep, FiO2. So the fraction of inspired oxygen in room air in this room right here is 21%, right? So if you take 21% times 760, what does that equal?
159.6.
How many?
159.6.
Close to 160. Let's just, I'm gonna round, and I might end up, I'm going to round with numbers that are a little bit higher or lower. So that means that oxygen in this room has a partial pressure of 160 millimeters of mercury. Okay? What's most of the atmosphere composed of?
Nitrogen.
Nitrogen's about how much? 78%. So if you take 78% of the atmosphere, 760, what's that? 760 times 0.7. It's weird writing on the wall.
592.8.
That's awesome. 593.
Yeah, 93
millimeters of mercury. So nitrogen in the atmosphere exerts a partial pressure. Does it have any physiologic function?
Just
No.
just to keep the pressure.
All it is pressure. It just exerts a pressure. Once the alveoli are open, it's not exchanged across the alveolar capillary membrane. It's just pressure that keeps the alveoli open. So it does serve a purpose. It exerts a partial pressure and it keeps the alveoli open with that pressure. That's it. We don't use it. It's an inert gas as far as the human body is concerned. What else is in the atmosphere? Argon. How much of the atmosphere is argon? How much?
Small number.
The book just says P other.
P other. It's less than 1%.
Yeah.
And a little bit of carbon dioxide.
Yeah.
So,
0.03%.
so if you take the amount of CO2, how much CO2 is there in the atmosphere?
So it's 0.2 millimeters of mercury.
Yeah, so it's 0.2 times 760. What pressure does carbon dioxide exert?
5.02 or something.
152.
What's point two? Actually, I think it is. It's 0.02.
Oh, okay, 0.02.
Yeah,
Might
0.02
even be
times
less than
760.
Yeah, 15.2.
Still that's 0.002.
It might be 0.00. Because what I'm trying to do is I'm
It
trying to
would be
get this to add up
1.52.
to. So if it's 0.2, then that means we'd have to make it a.
Yeah, that's 1.52 millimeters.
Is it? So it's 0.02 is 1.5 millimeters of mercury. And then the other one is argon, less than 1% times 760.
Oh wait, it is different then.
What partial pressure does argon have?
Doesn't say.
It doesn't say.
It doesn't give
It
us
just
that.
says other.
Other.
But all the others have 7 millimeters of mercury combined.
Yeah.
I don't know.
So you add all those up together, 160 plus 593 plus 1.5 plus 7, what does that give us?
1.5 plus 7.
Should be 760.
Yeah, it should be close
Yeah,
to
it's
760.
761.5.
Okay.
Close enough.
So the illustration is that it's an example of Dalton's law. Dalton's law is the sum of all of its partial pressures. So the atmosphere that we breathe in and out is composed of oxygen, nitrogen, carbon dioxide, and argon. And that you add those all up, and it equals the barometric pressure, right? So Dalton's law is an example of the law of partial pressures. You add up all the pressures in the atmosphere, and some of them are inert, some of them don't have a physiologic function. The one that we care about clearly is oxygen. So when we get to oxygen, trying to understand how we diffuse oxygen across the alveolar capillary membrane, it moves by diffusion. So if you have an alveoli and a blood vessel past the alveoli, remember the way I often draw it is as a one alveoli unit. But there's an alveoli in front, there's an alveoli in back, there's an alveoli to the side, there's an alveoli kind of in the front right, front left. So they're all around. And so I'm drawing a model that illustrates one alveolus of 300 million and recognizing that the surface area going on for gaseous diffusion is it's not infinite, but it certainly is exponentially larger and larger the further we get into the tracheobronchial tree. So if we take the amount of oxygen then and we put it into the alveoli, we should be able to get an idea of how much gas is there, so we can diffuse across how many layers? Did you read that in the text?
9 layers.
9 layers of, and I don't think that it's important that we
Fluid and tissue.
name each one, but if you've got the alveolar surface area, the alveolar epithelial, you've got the interstitial space, you've got the endothelium of the blood vessel, you've got the basement membrane of the blood vessel, you've got the plasma, and then finally you get to the endothelium of the red blood cell, and then it finally combines with hemoglobin. So the point is that it goes from this area of greater concentration to lesser concentration through 9 layers. That's pretty significant, and then combines eventually with hemoglobin to create oxyhemoglobin. So it does it by virtue of the partial pressure, the pressure that's in the alveoli, and that will always be a function of the FiO2. Well, you've already started in lab to talk about cannulas and masks and non-rebreathers and really devices to deliver oxygen, right? So what they do is they change the FiO2, thereby changing the partial pressure in the alveoli and diffusing higher and higher amounts of oxygen across the alveolar capillary membrane. The reason we would do that is because of disease and pathology that causes collapse, that causes atelectasis, that causes pneumonia, bronchitis. All of the diseases functionally impair the alveoli such that PO2s go down, and then you put that oximeter on their finger, what happens to the oximeter if PO2s are going down? Saturation goes down too. That's the point. So if the partial pressure goes down and we don't diffuse enough oxygen, the saturation of the hemoglobin goes down, and then we use that as an assessment for gas exchange, for oxygenation. And so their skin isn't pink anymore. Like when a baby's first born, how many babies are cyanotic? 100%, every last one of them. Because none of them are exchanging oxygen. They get the first couple breaths of air, and they pink up eventually. After about 2 or 3 or 4 minutes, they'll pink up. Well, they're pinking up because the partial pressure of oxygen is getting higher and higher and higher in the tissues. Right? So we assess color by indirectly relating it to oxygen and gas exchange. We assess the finger oximeter with the ability to move oxygen across the alveolar capillary membrane. We draw a blood sample and we directly measure the partial pressure. That's where all these numbers come from, is we're using them as assessments to how well they're going across the alveolar capillary membrane. When we get a chest x-ray, we're looking at areas of the lung that might be impaired. If we've got a white area of the lung, it means you're not exchanging gases in those areas, and we have to figure out ways to either mobilize secretions like you've done with postural drainage, to open up and expand closed alveoli with incentive spirometry and things like that. And in disease states like ARDS, put tubes into their lungs, expand their alveoli, and do it artificially, changing the FiO2 simply to improve this process, gaseous diffusion across the alveolar capillary membrane. Okay? So everything we do is a result of this process. So we don't talk about it on the surface. We talk about disease states and hypoxemia and other things that are relative to the ability to diffuse gas across the capillary membrane. Okay, does that make sense? Let's see. So in order to get an idea of how well we're moving gas across 9 layers of tissue. First thing we have to do is we have to get it in through our mouth. And so before it gets to the alveoli, it goes into the upper airway. It interfaces with a wet, warm surface. And so even on the coldest day, when it's 0 degrees outside, and we walk outside and you take a breath in, you're breathing air, cold air, dry air from the environment. You know, depending on, in Utah, it's fairly dry. If we were in Atlanta, a lot of humidity in the air. Does anybody know the difference between humidity and aerosol? You're producing aerosol with nebulizers, right, in the lab. What can you see about the aerosol? You can see it with your eyes that it's water particles, right? So aerosol is particles you can see. Humidity is water you cannot see. Okay? So here, what's the humidity today outside? It's not very, well, it rained a little last night, right? It might be 10% or 15%. But can you see the water vapor in the air outside? We really can't. So in humid areas, humidity is high. In dry areas like Utah, humidity is very low, but we can't see it. So when cold air, even on 0 degree days when it's snowing outside, you go out and you breathe that air in. You have to add water vapor to it. So by the time it gets to the carina, it's warm to body temperature. How many degrees is that? Almost 100. So you have to add energy. Your body has to add energy to get water in there, and then it warms it. It warms it to body temperature, and it adds 100% relative humidity. That's called absolute humidity. Okay. So if we warm it to 100 degrees and we add water vapor to it, then we have to account for it. So when we breathe it in, then we're going to add water and we're going to add heat. So you take the barometric pressure at sea level, 760 millimeters of mercury. That's barometric pressure. So you've heard them announce the barometric pressure on the weather reports, right? Around here it's around 640. But when a storm comes in, what happens to the barometric pressure? Drops. Yeah. Usually you can tell because when the front comes over, the winds change and the barometric pressure drops. So the barometric pressure goes lower than that when storms come in. But then we start seeing asthmatic patients come into the hospital because of that drop in barometric. Some of them are very sensitive to drops in barometric pressure. So if 760 is the barometric pressure at sea level, storms come in, that would drop. When we inhale that air on a dry day, we have to warm it to 100 degrees, 98.6, and we have to humidify it to 100% so it gets down into our pseudostratified ciliated columnar epithelium. So we have to, if we warm it to body temperature, which is 98.6 degrees centigrade, what is it, Kavi? What's body temperature at centigrade? 37. So at 37 degrees, and there's a table up on page 187. At 37 degrees, which is normal body temperature, we add water vapor to it, and it exerts a partial pressure of 47 millimeters of mercury. So that's the pressure of 1 liter of gas that when we add it to inhaled air. You breathe it in, every liter of fluid has a partial pressure of 47 millimeters of mercury. That table also suggests that absolute humidity is 44 milligrams per liter of water. So in order to get 47 millimeters of mercury pressure, every liter of gas adds 44 milligrams of water to make it absolutely 100% humidified. And that's what your body does, is it adds humidity to the air you're breathing in on the coldest day. At lower body temperature, so it's just giving you 35, 30, 27, 25, 20, you can see that it takes less water to be 100% saturated. 39 milligrams, 30 milligrams, 25 milligrams, 23 milligrams. Can you see where that's? So what it's telling you is that the warmer a gas is, the more humidity it can carry in vapor. And that vapor exerts a pressure. So I want to make sure that you don't mix up 47 and 44. The numbers are pretty close. Water exerts a partial pressure of 47 millimeters of mercury, and that carries physically 44 milligrams of water vapor in every liter we breathe into our lungs.
Can you say that one more time?
Okay. Water vapor, so 1 liter of air that we breathe into our lungs combines with 44 milligrams of water, and that exerts a partial pressure of 47 millimeters of mercury. So don't get the 44 and the 47 mixed up. I'll write a question that'll try to help you to remember that. Okay, so at body temperature, at 37 degrees, water vapor exerts 47 millimeters of mercury pressure. And then
44 milligrams per liter.
and it holds,
Jesus.
and it holds 44 milligrams of water in that liter of fluid, liter of gas. Does that make sense?
Mhm.
So it exerts a partial pressure, 47. It contains water vapor, 44 milligrams. Got it?
Yep.
You weren't kidding about deep stuff.
Well, this isn't half of it.
We're just scratching the surface.
We're inching up to it.
All right.
So the air that we breathe in, every liter of gas we breathe in, we add water vapor to it. That's the point here.
Okay.
The warmer the body temperature, the more water vapor it carries without raining out. Now, have you ever been in the hospital where patients are on ventilators and we warm up the ventilator circuit to 37 degrees, but it goes from the humidifier out to the patient, and in the patient circuit there's always water vapor? It's because the outside temperature isn't 37 degrees, it's 22 degrees. And so all the water that was in vapor when it came out of the humidifier rained out because it doesn't carry as much water vapor in that tube in the room temperature. In our body, it's 37 degrees. So it carries more water vapor. I mean, it physically holds more water without raining it out. Okay? Your inside of your body, you know, what is it, 70% of your body is water. So your body adds water. I mean, the purpose of your turbinates is to increase surface area, to add water to the air you're breathing in. All that squamous epithelium up in the upper airway and the nasopharynx and the oropharynx is to add water, and it does it very efficiently. So it adds water. That water exerts a partial pressure, and we know exactly how much water is in the air that you breathe, depending upon the temperature of the patient. Okay, so we're going to assume that a patient's 37 degrees and it exerts a pressure of 47 millimeters of mercury, and that it holds 44 milligrams of water in it. So the barometric pressure minus water vapor pressure times the FiO2. So the FiO2 is the fraction of inspired oxygen. At room air, in this room, there's 21% of oxygen in this room. We subtract, so we can do that part of it. Barometric pressure is 760 minus 47 is 713 times 0.21. What is that, Jimmy?
Sorry, say that again?
713 times 0.21.
$150.
Thank you. 150, 50? Great. So that just shows you that we've taken dry gas. So here's the oxygen here in dry gas in the atmosphere. We take 21% times 760, we got 160 millimeters of mercury. We inhale it into our body, and it's not 760 now, it's 750 millimeters of mercury because I had to account for the water vapor that we added to it.
150.
Okay? So that's where that water vapor pressure comes from, is we have to account for it and take it away from barometric pressure. So this is dry gas. And this is wet gas. We're inhaling this. This is inhaled gas. And we ended up with a little bit less than what we did with dry gas because we had to make an accounting of what we breathe into our lungs. So 150 millimeters of mercury. But then what the alveolar gas equation tells us is that we have to account for how we're ventilating. So remember, oxygenation is about how much oxygen there is. Ventilation is about how much CO2 there is. CO2, if we hyperventilate, what happens to CO2? It goes down, that's right. We exhale more CO2 to the environment. So we have to account how much we're ventilating. And so we take the pressure of arterial CO2, how fast we're ventilating, times a factor of 1.25. That will always be, 1.25 is equal to 1 plus 1 minus the FiO2 divided by R, which is 0.8. That's the VO2 divided by the VCO2, and it's always, normally it's about 0.8. So instead of doing this,
Yeah.
Yeah.
That's better.
Like that?
That's so much better. I was like, now we're getting a little more
was
deeper
nice.
now.
right,
Okay.
so I'm trying to give you a little
Or
bit
the
of a
last year.
shortcut. We're going to use 1.25 as the factor for understanding gaseous exchange across the alveolar capillary membrane. So barometric pressure minus the FiO2, barometric pressure minus the water vapor pressure times the FiO2 minus the PaCO2, arterial carbon dioxide, times a factor of 1.25. Normal CO2, does anybody know what it is?
Normal CO2?
What would we consider to be normal CO2?
About 40.
Good, yes indeed. We understand a range of about 35 to 45 millimeters of mercury. That's a normal partial pressure of CO2. It's a range. But right in the middle is 40. So if you take 40 times 1.25, that's 50, right? You can say yes on this one.
Yes. Right.
40 times 1.25 is indeed 50. So you've got the amount of oxygen in the alveoli, plus in here you've got to account for O2 and CO2, because CO2 is coming from here and going into the alveoli, right? So in the alveolar structure, granted there's nitrogen here, and that's helping to keep the alveoli open. The partial pressure in there is keeping the alveoli open. But the only thing the human body needs is oxygen and carbon dioxide. So oxygen's coming in as a partial pressure from the environment. Carbon dioxide is higher after metabolism occurs in the tissues and now is diffused across the alveolar capillary membrane, and we exhale that to the environment. That partial pressure is about 35 to 45 millimeters. We'll say that 40 is right in the middle. 40 millimeters of mercury. So we're exhaling, we have higher concentration here, it diffuses across the alveolar capillary membrane, we exhale that to the environment. So if you hyperventilate, you're taking more of that CO2 and you're exhaling it out to the environment because your alveoli are hyperventilating. Make sense? So CO2 and O2 are the things we're making sense of in the alveolar environment. PO2 is 150. Ventilation normal at 40, we used right in the middle of that range, 35 to 45. We said 40 times 1.25 was 50. 150 minus 50 is a P big A O2 equals 100 millimeters of mercury. So what we've just done is we've suggested that at sea level, the PO2 in every one of your 300 million alveoli is 100 millimeters of mercury. That's how much O2 is in every single alveoli at sea level. And so it's sitting there as a partial pressure. The PO2, I don't know if, I think they do in this chapter. Yeah, they do. So what's interesting about that, so you've got a partial pressure of 100 sitting in your alveoli, all 300 million alveoli. When we make sense of the diffusion of gases, we've got a PV with a line over it, that's called mixed venous, okay? Mixed venous gas. So the pressure of mixed venous O2 is somewhere around 40 millimeters of mercury. The PV CO2 of mixed venous gas is somewhere around 46 millimeters of mercury. Okay, and this is just from a diagram over on page 189.
189 or 180?
So what we're doing is we're setting up a diffusion gradient. What's the partial pressure of oxygen in the alveoli? 100. What's the partial pressure of blood that's coming back to the heart from the right atrium, left ventricle, the right ventricle, and out into the lungs? PO2 is 40. There's a diffusion gradient of 60 millimeters of mercury. So where does oxygen go? As this blood comes past the alveoli, oxygen has to go into the blood. There's a diffusion pressure difference of 60 millimeters of mercury. So diffusion is the process of moving from a higher concentration to a lower concentration. So if the alveoli have a concentration of 100, the blood has a concentration of 40, oxygen will necessarily go from the alveoli to the blood vessel. Make sense?
Mm-hmm.
It's got a pretty high pressure gradient, 60 millimeters of mercury. So it's going to really go across there. CO2, on the other hand, if you said 40 was the normal that we used in our alveolar gas equation, if the CO2 here, I'm going to use a different color. If the CO2 is equal to 40, that's the middle between 35 and 45 millimeters of mercury. And I've got a CO2 in mixed venous blood that's come back up from the rest of the body, come up to the right atrium, the right ventricle, and is now being pumped out to the lungs. That blood has a partial pressure of 46 millimeters of mercury. I have a partial pressure of 40 in the alveoli. What direction does CO2 go? Yeah, it goes from the vessel into the alveoli, and that's what you exhale out. In this most simplistic form. Now, it's not that easy.
Yes,
No,
yes,
I'm
it
going
is.
to tell you, it's not that easy. But for right now, that's a good explanation of how oxygen goes into the blood and CO2 goes out of the blood. Okay?
Probably not that easy, you mean, when it switches the,
No.
back from bicarb to hydrogen?
Yes,
back?
that's it.
Okay.
But the bicarbonate in the hydration of CO2
Yeah,
yields carbonic acid and bicarbonate, and so
and it switches back to CO2.
yeah, exactly. We'll talk about that. We'll talk about that. But for now, in this most simplistic form, you can see that we've set up pressure gradients and that oxygen goes in and CO2 goes out. Okay? And it's based upon pressure gradients. So this PO2 of 100, in fact, at sea level, we always suggest that the P, so what's the difference between P big AO2 and P little AO2?
Alveoli and
arterial.
This is alveoli, so what's in the alveoli? This is what actually diffuses across into the arterial blood, PaCO2. So at sea level, we always suggest that the PaO2 is equal to 80 to, I'm sure you've talked about that.
Yeah, we did.
So why do we say 80 to 100?
The range.
Ranges.
It's a range, absolutely. We've just calculated that it should be near 100. 100 is closer, 100 is where it should be. But we'll accept this range, just like CO2, 35 to 45, oxygen, 80 to 100 at sea level.
The elevation will change.
Yes, indeed, we'll do that. So the P little AO2, the partial pressure of arterial oxygen, is 80 to 100. So every time you think about PO2 for board exams, for any example, we're going to understand it to be 80 to 100 normal. Okay, we live at elevation, so our normal is a little bit lower, and we'll calculate that. But for right now, 80 to 100. If I ever ask you the PO2 or Lindsey Jones asks you what the normal PaO2 is, you'll say 80 to 100. Okay, and the reason is because a partial pressure of 60 millimeters of mercury yields a saturation of 90%. So we're thinking in ranges anyway. 80 to 100 normal partial pressure of arterial oxygen. And it's because of what's available in the alveoli. Okay, we've just calculated it at 100. So if you have a few alveoli that are collapsed in the front, this one's collapsed in front, and you've got one functioning, maybe your PO2 ends up over here about 81 millimeters of mercury. It's not 100, because you've got some collapsed alveoli, you've got a little bit of atelectasis in the back, or pneumonia in the right middle lobe, community-acquired pneumonia. And so you don't exchange, all of the alveoli don't have oxygen, so the average of the PaO2 is around 81. So we're allowed that range. That's still a saturation of 92 or 93 or 94%. So a PO2 of 81 is still a saturation of 94 or 95%, which is still adequate. It's still life-sustaining. But if enough of the alveoli are closed and collapsed, and you've got a huge broad spectrum alveoli where this whole lung is collapsed, and maybe you've got some collapse on the other side, now your PO2, because you have fewer surface area, fewer alveoli for gas exchange, maybe your PO2 comes back 60. Or let's make it even worse. Let's make ARDS, and it's 52 millimeters of mercury. So if the lungs are diseased to the point where your PO2 now is 52, your saturation is much less than 90, you can make judgments about the severity of alveolar collapse and or gas exchange, right? And so that's when we start to think about adjusting the FiO2. Is if room air it's at a PO2 of 80 to 100. Well, let's do it for a PO2 at our elevation before I jump too much ahead. So that's sea level, and that's where we get our normals from. That's how we understand the alveolar gas equation. Okay. So the first exam, by the way, is the first 4 chapters, right? I always add a bonus question on the exam. It's worth 10 points, and the bonus question is always a calculation.
Yes.
What have we calculated in the first 4 chapters?
This.
Gas exchange.
I'm telling you.
Alright. Got a note.
Okay, so the barometric pressure in Salt Lake City is 600, and right now after this storm just passed, it's 630 millimeters of mercury. Normally it's around 640, but the barometric pressure is 630. What do we have to do if we inhale gas? We're going to subtract off water vapor pressure. So how much is that?
47.
At 37 degrees, it's 47 millimeters of mercury. Times the FiO2, if we're breathing room air here on the Wasatch Front in the School of Dentistry on the U of U campus. CO2 is 40 times 1.25. 40 times 1.25 is 50. 630 minus 47 is 583.
Yeah.
583 times 0.21 is what?
Sorry.
583 times 0.21
122.4.
minus 50, 74. Right now, Kavi
Yes.
and Hannah and Armando, your alveoli contain 74 millimeters of mercury.
72.
72? Okay. 72 millimeters of mercury in every open alveoli right now in your body. 72 millimeters of mercury. It's exerting a partial pressure here at the Wasatch Front with that barometric pressure and that CO2 if we're breathing normally, if we're not hyperventilating now.
Man. Cool.
has a partial pressure of 72 millimeters of mercury in your alveoli right now at this moment. All 300 million of them. Now what if we're hyperventilating? What happens to CO2?
Well, not
It drops. So let's say your CO2 is now, we're really hyperventilating, 20 millimeters of mercury. Normally it's 35 to 45, we're gonna say it's 20. We're really blowing off CO2. 20 times 1.25 is what?
30.
Is it 30?
What?
30?
20 times 1.25?
8.
There.
25.
25. So
Yeah.
122 minus 25 is a PO2 of 97.
So,
What happened? It's not 72 if we hyperventilate.
No, I do.
So in the alveolar structure, if I hyperventilate and drive off my CO2, I make more room available for a PO2. By hyperventilating, I'm blowing off CO2, which makes my alveoli accommodate more oxygen. We can increase our PO2 by hyperventilating. So remember, when we talk about certain diseases, we often say that a patient becomes tachypnic and tachycardic, right? They're tachypnic, they breathe fast to improve their PO2. When they get blue and cyanotic and they're uncomfortable and they can't breathe, what do? They compensate by breathing faster. And that improves PO2. So they're compensating. By blowing off CO2, they're allowing more oxygen in their alveoli. What about if a patient goes into respiratory failure? They go into respiratory failure and now this CO2 is 70 millimeters of mercury, so they're hypoventilating. If they hypoventilating, Jimmy, what's 70 times 1.25?
87.5.
87? So almost 88. What's 122 minus 88?
34.
34. So if I'm hyperventilating, I drive off my CO2, I make more room for oxygen. If I'm hypoventilating, CO2 goes up because I'm not exhaling that out to the environment. The alveoli has to account for that CO2 and my ventilation pattern. Now it's 88 and my PO2 can only get up to 34. So breathing in and out is kind of an important thing, don't you think? It influences, hyper and hypoventilation influences how much oxygen is available for gaseous transport. Interesting, eh?
yeah.
So normally we'll consider that we're breathing 35 to 45, normal PCO2 of 40. But you can see how it influences oxygen availability and perhaps even delivery. If we're hypoventilating, CO2 goes up, it doesn't make as much room in here available for gaseous transport. If PO2 is 34, then I don't, So the goal of diffusion then, moving on from the alveolar gas equation and allowing for the influence of oxygen and carbon dioxide and how we ventilate, whatever's in here should get into the pulmonary blood vessel. So if the mixed venous gas has a PO2 of 40 and a PCO2 of 46 millimeters of mercury, we would expect that if it came in contact with this alveoli, that our PO2 would match that. It would reach equilibrium. So some people think that gaseous diffusion, when I talk about this subject, that it should come to an equilibrium. And so if this is 40 and if this is 100, then we should reach the middle at, what's exactly the middle, 65? 70. So the PO2 isn't 70, it's whatever it is in here. Okay, so I don't want you to think that whatever's up here and whatever's down here, it reaches an equilibrium in the middle. It doesn't. Whatever's in the alveoli, it diffuses to that capacity. Okay, it's not an average. It's whatever's in here should get into here, all things being normal. And whatever CO2 is in here should get into here. So the PO2 should be 100 at sea level. It should be 40 millimeters of mercury for carbon dioxide count.
So with the elevation
Yeah.
and acclimating, what does that exactly mean when you're acclimating?
Well,
Because then your body doesn't have to like hyperventilate as much.
right. So what you're doing, if we go back to normal values, we said this was 72, right?
Yeah.
So now you've got a PO2, a big AO2 of 72 millimeters of mercury,
Yeah.
which means that what's available here is 72 millimeters of mercury.
Yeah.
So what you do is you build up red blood cells through erythropoietin. That's not necessarily hypoxemic because it still offers a PO2 of saturation of 90%. So you're still very well saturated. Your hemoglobin carries 90% oxygen on it. So to acclimatize, if you're going up to Everest, let's give you an example of Everest. What's the barometric pressure up there at the top of the world? 29,028 feet. 29,028 feet.
See
Is
like
that it?
380 or something?
Yeah, it's about 300. We'll say 380. Maybe on a good, warm, sunny, clear day, it's 380. What do you have to do to the air you breathe into your lungs? You have to
Subtract it out
add
way, but
water vapor to it. At 37 degrees, it's always
47.
47. 380 minus 47 is 333.
33. Yeah.
Times 0.21. 333 times 0.21.
60 or 70.
70?
Yeah.
Okay.
Yeah, 70.
So dry, it's 70 in the alveoli, but we have to account for ventilation. So what do you think you're doing up on the top of Everest where the partial pressure is much lower? You're hyperventilating a little bit. So let's say your CO2 is not 40, but maybe it's 30. So you're hyperventilating, it's causing you to breathe a little more. 30 times 1.25 is 38. 70 minus 38. 32. So the partial pressure of the alveoli at the top of Everest is 32 millimeters of mercury.
Dang.
Wow. Which means that if it reaches equilibrium, the PO2 is 32. What happens when your PO2 is 32?
Yeah, you're dying.
You die, basically. Yeah. If we were to take a helicopter from here and go up to Everest and drop you off, you'd be unconscious within a couple minutes. And you die. You die from high altitude pulmonary
You
edema.
should get to enjoy the scenery before you die, I guess.
It'd be nice and pretty, and it's so wide up here. Go to the light.
Take me away.
Go to the light. Yeah, exactly. So the PO2 is 32, and so what you do is they stay for months up there, and they acclimatize by building up red blood cells. So their PO2 might be 32, but their hemoglobin, we'll talk about this in another chapter, but their hemoglobin is 20 grams %, not 15.
So what happens if they come back down? Does it cause any
The
toxicity?
coming down is the best possible thing.
Well, I mean, like, they're acclimated at that.
Yeah.
They come down too fast.
Over time, they'll release red blood cells.
But I think what she's trying to ask is like, if we were at the bottom and dropped off at the top, we have problems.
Yeah.
What if we're at the top and then dropped off at the bottom?
We'd be fine. Our heart just works harder to pump thick blood around.
No, just itself.
But over time it would adjust. So there's no problem coming down. The problem is going up. So we've just illustrated partial pressures at sea level, at 5,000 feet, and now at 29,000 feet. It influences gaseous exchange.
Nice and rich.
I was gonna ask, so if the PaO2 in Everest would be 32, so even if we've been there for months and acclimated, how does it make it through the capillary when it's 40 in like the Venus?
They're on oxygen.
Yeah, they're usually on
They're on
oxygen.
oxygen.
So this is at the end of normal metabolism and what the tissues had to extract. So under normal conditions, it'll extract what it needs to. In fact, that becomes another topic. We extract 5 volumes % of oxygen. and we leave 75% of it attached to the hemoglobin, and it goes back.
So would the venous O2 be less than Everest as well?
Yes.
So that allows us